The voice in this video is AI generated. Hello guys, I am Tomas and in this video I am going to show you program I wrote almost 1 year ago. I call it Token because back then I didn't want to spend time thinking of a proper name. Token is subchannel code for thermal hydraulic calculations of reactor core. For now I want it to be able to calculate water-cooled reactors, primarily Western PWR type reactors and Russian VVER type reactors. This methodology can be also used for simplified calculations of BWRs, but there are much better options for those. Subchannel approach is one of the most frequently used methods in reactor thermal hydraulics. It is used for fast calculation of important parameters such as temperature or void fraction. These parameters are often compared to acceptance criteria during accident analyses or during campaign optimization. The easiest problem to which subchannel approach is applicable are two parallel, laterally interconnected channels, or rather subchannels. Water flows via entrance into test geometry. Each subchannel has different dimensions and thus different hydraulic resistance. This makes water flowing from one subchannel to the other. So even if we have the same mass flow in both channels at the beginning, we will end up with different mass flows at the end. This is why this problem is sometimes also called flow split problem. First we need to set up test geometry. For this exercise we will use geometry similar to typical PWR fuel. We will use fuel pins with 10 mm diameter and 12 mm grid pitch. Test geometry consists of two channels, interior and edge, defined by 4 fuel pins and physical boundary. It is convenient to calculate all necessary geometrical parameters numerically. Here is demonstration of numerical calculation in program Inkscape. I drew geometry and numerically found centers of mass for each channel, areas of channels, gap length, distance between centers of mass, heated and wetted perimeters. Then I inserted all geometrical parameters into input file. Definition of subchannels is easy, since there are only 2 of them. In the columns are from left, number of subchannel, flow area, wetted perimeter, heated perimeter, grid type, which can be either square or triangular, and type of subchannel, which can be interior, edge or corner. Definition of gaps is even easier. First 2 columns define which subchannels are connected with this gap, then we have gap width, distance between subchannels, and finally some parameter which will be added in future. For now it is 0. Since we do not have any heat sources in this example, we can leave heat structures and radial profile empty. Axial profile can be left as it is. We also don't need any spacer grids in this example. Now we can choose what settings do we want to use. We can choose whether to use gravity or not. Then we can choose source for water steam parameters. In this example I will use industrial formulation of IAPWS, IF97. Alternatively we can use some simplified model. Then we can set up correlations for single-phase friction. For simplicity we will stay in turbulent regime and we will use Blasius correlation. This makes few setting like grid type or surface roughness irrelevant, but it will allow us to easily check our results. Settings important for more complicated correlations or for two-phase flow can be ignored for now. Next we need to set up calculation control settings like method or numerical solver. For now important will be number of axial nodes. Most important settings are operational conditions. Here we can set up axial length of our geometry, channel orientation, pressure, temperature, flow rate and power. In the folder we have currently 3 files: input file, some Python code for results visualization, and our main code token. In the input file, I set number of axial nodes to 50 and total axial length to 5 meters. The Python file is some simple code which will plot desired columns from output file into a chart. This way, we can simply visualize calculation results. Now we can run token. We can see that code execution is very fast for this simple example. Program will show some useful information. Most important is convergence table for individual conservation equations and execution time. In this case it was 0.15 seconds. The output file is organized as multiple tables. First we have tables for each subchannel. We can see table of results for subchannel 1. There are multiple columns in this table. Each column corresponds to single variable. Each row represents one node. Under the table for subchannel 1, there is table for subchannel 2 and then 2 more tables for crossflows in gaps. Right now, we will plot mass fluxes in each subchannel, which are in column number 9. When I run Python code, I will get chart. We can see that both curves start at around 1637, first curve ends a bit higher, at around 1647 and second curve ends a bit lower at 1626 kilograms per second per squared meter. Now we have some results to work with. The first question we have to ask with new code like this is whether our code really calculates something meaningful or whether it is complicated random curve generator. We need to assess whether the code satisfies our initial requirements, which are defined by programmed mathematical operations. In other words, we need to check conservation equations. Questioning whether the code produce expected results is called verification. Questioning whether those expected results are related to real world is called validation. I will leave that part for another videos. Let's verify our results. First we will analyze the problem analytically. Then we can compare analytical results with numerical. We start with Darcy-Weisbach model of friction pressure losses, Blasius friction factor and Reynolds number definition. Model consists of 2 parallel, laterally interconnected channels. The inlet velocity is the same in both channels. One channel has higher hydraulic resistance. The different frictional pressure drops create a lateral pressure gradient. This drives flow from the higher resistance channel to the lower resistance channel. This causes mass flow rise in low resistance channel. Higher mass flow mean higher velocity and thus higher resistance. Simultaneously, pressure drop decreases in the high resistance channel. This continues until the mechanical equilibrium is reached when frictional pressure drop is the same in both channels. In the point of mechanical equilibrium we can start with pressure losses and mass conservation equation. After some work we can derive system of equations for mass fluxes in both channels. We can use input data and derived equations to evaluate mass fluxes. Now we can compare analytical results with numerical. We can see good agreement between these two calculations. Small differences are visible due to precision of used values. Now that we are familiar with the approach, we can be more precise. First, let us compare velocities, since those are small enough to have 4 decimal precision in output file. The agreement between calculation and analytical solution is again very good. Right now we are using 50 axial nodes. Each node represents 10 centimeters in our model. Let's see what will happen if we lower number of nodes to 10 nodes. Now each node represents 50 centimeters in our model. Let's do 2 more examples. If we use 200 nodes, each node will correspond to 2.5 centimeters, which is approximately 1 inch. And finally let's use 500 nodes. This way each node will be 1 centimeter long. Comparing all 4 plots, it is obvious that if we use very small number of nodes, our curve isn't very smooth. Small amount of detail on this curve makes it look a little squished at the beginning. This means that 50 centimeter long nodes are not very good approximation of infinitesimally small nodes. Obviously, if we want to see how significant this effect is for our nodalizations, we can compare values of velocity in some critical point, like 0.5 meter in this example. Now we can see that for this example, 200 nodes is perfectly fine and we do not need to waste processor power for finer mesh. Next question we ask ourselves in this video is, what happens if we will use longer geometry? As we can see, we are asymptotically approaching equilibrium. The accuracy is actually quite good considering precision of numbers I used for analytical solution. Relative error is 0.010% and 0.024% for both subchannels. That was the last example for today's video. Thank you for watching and I hope you enjoyed this little demonstration of token.